OK, so before we get actually started with new stuff, I want to see first if there are questions about anything we did yesterday. Nope. OK, so remember what we were talking about last time was quantum gates, reversible classical computation, and also basic quantum gate sets. And the one thing I didn't tell you was I listed a bunch of quantum gates, and maybe I should write down some examples of them again. So we had, for instance, the Hadamard. Which had this matrix. And you remember when we want to do a circuit diagram, we draw it like that. We had, for instance, a phase rotation. And C0 gate. Which gets drawn like this. The Toffoli gate. And of course, those are just examples. And of course, in principle, what we'd like to be able to do is to do arbitrary unitary transformations. And so you have to ask, are these sufficient? Do we need to look at more gates, or is that going to be able to get us anything? And so that's the problem of what is a universal set of gates. And so the first topic for today is what are classical and quantum universal sets of gates. So it turns out classically, what do we want to do? So classically, our goal is obviously not to do arbitrary unitary transformations, but to compute arbitrary functions. And it's going to be a function of n bits. And let's just say it's a function whose output is a single bit for at least for irreversible computation. And why is that sufficient? Well, if you have an output which is 5 bits, you can have just 5 such functions. The first function is the function whose output is the first bit. And the second function is the function whose output is the second bit. And the third function is output the third bit, and so on. OK? So it's really enough to consider functions that map z2 to the n. That's the space of n bits to z2. And of course, if we're doing this irreversibly, that's really all we care about. If we want to do it reversibly, then we just keep around the n input bits and add this as an n plus first bit. So because there's n variables here, and because we're dealing with bits, and bits have the property that whether x is 0 or 1, x squared is equal to x. OK? So what that means is that we can write an arbitrary function as a polynomial. And moreover, it's a polynomial where each variable shows up in any given term. It shows up to, at most, the first power. So it's a sum of products of subsets of these things. And of course, the coefficient, because we're over z2, is just 0 or 1. And obviously 0 means you don't include the term, and 1 means include it. Okay? So maybe the thing that wasn't clear about that I didn't really say is, why is it a polynomial? Well, it's because if we allow degree n terms, well, we can just kind of plug in every possible value and have a polynomial that interpolates those values, right? There's always, given a finite number of values, you can always write down some polynomial that will take on those function values, right? And I've just explained to you what all the possible polynomials look like. All possible polynomials look like on these n-bit variables. So writing that down, we want polynomials of degree less than or equal to n, and then each term is a product of a subset of the input. Now, that doesn't mean they're simple, right? Because a term could be an arbitrary subset of these. And how many subsets are there? Well, there's 2 to the n subsets, right? And so that's a lot of different possible terms in this polynomial. And moreover, how many polynomials do you have? Well, we have a subset of subsets, right? We could have any set of subsets that appear in this sum. So there's really a lot of such functions that we have to be able to compute. But because of this simple structure, it's not too hard to figure out a classical set irreversibly of universal gates. Irreversible. So it's sufficient just to have not and and. Why is that? Well, and remember, if you have the and of 2 variables a, b, that's equal to a times b. So if you want to make a monomial term that's a product of some subset of these inputs, what do? You simply take the and of all the variables that are in that term, right? And that gives you the product of all of those. OK, so that's how to make any single monomial term. But what about sums of terms? Well, this is where the not is going to come in. So of course, if you take the not of a variable, you can write that as a plus 1. So that would be a way to add in a constant term. And if you take the not of the and of things, this, if you calculate it, is the or. So that's one of those basic logic rules, De Morgan's law, I think. And you can just write down the truth table to see that this is true. And this you can calculate is equal to AB plus A plus B. And moreover, XOR, that's the sum. And this is the thing that we're going to want to use to add up different terms, right? We're going to generate monomials by using the and then we're going to take the XOR of them to add them up and make the general polynomial. And this you can derive then as A and not B, or not A and B. Right? Those are the two possibilities, that either you have A but not B, or you have B but not A. Right? And so these are all things that we can do. We can do the AND, we can do the NOT, we can do the OR. And so we can do the XOR. And so now we're able to do arbitrary polynomials, right? Because we can you know, like I said, pick out monomials, make them out of these ANDs. We can take the XOR of them. And then there might be a constant term that has the empty subset, that are no variables. Then we can add that by putting a NOT around the whole thing. OK? So one thing that maybe is worth noting is not going to be terribly important right now, and not really important later, but it shows up occasionally in the field of quantum computing, which is that different monomials can reuse the same variables. Right? And so what that means in this case is not a big deal, because I guess I'm assuming that we can copy classical bits. Of course, there's no cloning theorem says you can't copy quantum bits. And if you don't remember what that is, I'll review it in a few minutes. But in the classical case, that's kind of not very controversial. But it's kind of, in some sense, an additional primitive that's assumed here. Yeah. So then this is an irreversible set of a universal set of gates for irreversible classical computation. And so then what about for reversible classical computation? Well, for reversible, we need kind of the same things, but now we have to do them in a reversible way. And of course, the reversible version of the AND is the Toffoli gate. Well, OK, let me not say that that's the whole thing. So we also need some other options. And in particular, if we include the ability to create 0 and 1 ancillas, then the Toffoli gate can also do the NOT. How can it do that? Well, remember, it's a 3-bit gate. And so if we put in 1, 1, A here, what do we get out? We get 1, 1, A plus 1, which is not A. So that lets us do NOT. And we can certainly do the AND, because that's kind of how this was designed. And that, remember, is by putting in the 0 here. So we get A, B, A, and B. OK? So we're getting back our universal set. OK? So are there any questions on this? OK, so that's a universal set of classical gates. I guess one thing I want to point out, it turns out that, so this is the reversible set for, sorry, universal set for reversible gates. And it involves a 3-bit gate. Whereas the irreversible set, it was enough to have 2-bit gates. And it turns out that there is no set of universal reversible operations that uses only 2-bit gates, or up to 2-bit gates. You really need a 3-bit gate in order to make that work.
Question?
Yeah.
Is there a way to make a bigger set but have 2 bits? No.
No, that's what I'm saying. Is that I mean, even if you include all possible 2-bit gates, it's not universal. I mean, the reason is that there's just not that many reversible 2-bit gates. They're kind of, there's XOR, there's swap, and then there's combinations of those and with NOT, basically the 1-bit gates. OK, so let's go to the quantum case now. So now the goal is to do an arbitrary unitary transformation. It's n qubits, so we have a 2 to the n dimensional Hilbert space. So we want something from u2 to the n. Of course, the global phase doesn't really matter, so you could also think of it as su2 to the n. It's kind of some ambiguity. It depends on exactly what you're doing, whether I mean, usually the global phase is there in terms of the gates that you write, so it's really an element of this, and it might or might not be an element of this, but really what you want is the projective Hilbert space, but that's a complication that I don't really want to get into. OK, so we want to get an arbitrary unitary. But there's actually still some ambiguity as to how you want to do that. So there's two options. So you could go for exact universality, where you can get exactly every unitary. But if you think about it, that's really demanding too much in a lot of cases. Really, it's sufficient if you can get arbitrarily close to any unitary, right? Because there's not really any way. If you get epsilon far away, it's going to be very hard to distinguish that from the actual gate you wanted to perform. And when you do your computation, the measurement outcomes will be almost the same. Now, there's a question of how close epsilon has to be. But remember, I'm saying you can get arbitrarily close, so you can make it as small as you like. So this is approximate universality. And what this means technically is that the set of gates should be dense. Set of gates that you can achieve should be dense in the unitary group. Or again, su2 to the n. OK? OK, so if you want exact universality, then kind of the most common universal set of gates you'll see is C0 and arbitrary single qubit unitaries. There are other universal gate sets in the literature, but this is a pretty common one. Or some version of this, some kind of 2-qubit gate that's equivalent to C0, like the controlled Z gate or something like that. OK? And when you do this, it's not at all obvious, and I'm not going to try to prove it because it's a bit complicated. But once you do this, you can put these single qubit gates and the C0 together to get exactly any unitary on n qubits. OK? And then approximate universality. Again, there are different gate sets in the literature. But here are some common ones. So one is this. So this, of course, is an infinite set of gates because you're doing arbitrary single qubit unitaries, U2 gates. This is a finite set of gates. And so what does it have? It has the Hadamard in it. It has this, this phase rotation, which is the square root of z. So it's the 1i diagonal gate there. And it has the Toffoli gate. And the idea is that even with these finite, this set of 3 gates, it's not really 3 gates because you're doing this on n qubits. And so there's n qubits that you could do these things on, and n q's 3 sets of qubits. Really more than that because the order matters a little bit. 3 times n q's 3. That gates, sets of qubits that you can do the Toffoli gate on. But the point is, it's only a finite, with n qubits, it's only a finite set of these things. And yet, by multiplying them together, you can get arbitrarily close to this infinite set of things. right? So the things you get here are countable, but they can still be dense in u2 to the n, which is uncountable, just like the rational numbers are dense in the real numbers. And the way that works is that these gates don't commute with each other. And so by doing them in different orders, you can get arbitrary combinations. You can get things that are very close to the identity, for instance. OK? Remember I mentioned that classically the Toffoli gate, you needed to have 3-bit gates in order to do universal set for reversible computation. But notice that in the exact quantum case, I could just make do with 2-qubit gates. So that's an improvement over the classical case. And again, it's taking advantage of the kind of extra range of non-commutativity. Classical gates are also not commutative, but quantum gates, you have kind of more options. And so you can manage with just 2-qubit gates. But that makes this gate set a little undesirable because you're going back to 3-qubit gates. But it turns out that there's a kind of a similar set, which is uses the C0 gate instead of the Toffoli gate, but then it uses the square root of this gate, so the 4th root of the sigma z operation as a phase gate. And again, this is a universal, approximately universal set of quantum gates. OK? So there are questions on this. Yeah?
So the Toffoli gate here is a 3-qubit gate, right?
Yeah, 3-qubit gate. This is the quantum Toffoli gate. Yeah.
For the exact set, you have C0 and any single?
Yeah, arbitrary single qubit unitaries.
Arbitrary, so you can choose just one? Or?
No. So so first of all, you know that if you want to get exact universality, because it's an uncountable set of gates, so any circuit you do is going to have a finite number of gates in it, any particular circuit, right? So if you have only a finite set of gates in your universal set, you only can generate the products of these things will only be a countable set. So if you want an uncountable set, you need this to be uncountable as well. And so in order to get a kind of an arbitrary unitary, you do need, I mean, it doesn't really have to be completely arbitrary unitaries. It's enough to have, say, rotations about the x-axis and the z-axis. But you do then need arbitrary angles. OK. Yeah?
Do I still need to be able to add ancillas?
No. Well, let's see. Let me think.
For a single qubit.
So in this case and in this case, you definitely do not need ancillas. In this case, I guess you do, because like you couldn't do 2-qubit gates without that, right?
So I can get any single qubit gate using H and R pi over 2 or
Yep.
R pi over 4?
Oh, sorry, no. So with H and R pi over 4, you can, yeah. Not with H and R pi over 2. That's just a finite set. Anything else? OK, so these are universal sets of gates, classically quantumly, which means that no matter what function, no matter what unitary, we can get it by building some potentially big circuit out of these universal sets. But there's many possible unitaries and many possible functions. And some of the circuits we need will be really big, like exponentially big in the number of qubits or the number of bits. And actually, that's unavoidable. And you can just prove that by simply counting. Remember, I said, how many functions are there? Well, it's not just 2 to the n. It's 2 to the 2 to the n, because you could have any subset of subsets. And there's no way you can get, if you only have circuits of size 100, well, you only get like n squared to the 100 different possible gates, which is way smaller than 2 to the 2 to the n. And if you have circuits of size n, even that's not enough, right? So you actually have to go to exponentially sized circuits in order to be able to build arbitrary functions. But some functions and some unitaries you can make with many, many fewer gates. And that's the whole point of the study of algorithms and complexity, is to understand what functions you can make efficiently with a relatively small number of gates, and which ones require many, many gates. OK? I guess one thing that I won't really have time to go into, but is worth mentioning, is when you're dealing with approximate universality, there's another kind of scaling factor you have to worry about. When you're dealing with exact universality, the only question is how many qubits do you have, and how many gates does it take to make something of that size. But with approximate universality, you want to get within epsilon, right? And so the smaller epsilon is, the harder that's going to be. But it turns out that that part is efficient, that you can get to within epsilon with something that's polynomial in the log of 1 over epsilon. So you can really get very close with relatively little effort, at least in the limit of big circuits. OK? So any more questions about universality? Yeah.
If epsilon is a small number, then log of epsilon is that's a negative.
Log of 1 over epsilon.
Oh, 1.
Yeah. OK. OK, so next topic. So now I want to review the no cloning theorem and start some simple quantum protocols. Probably some of them you've seen before. And so the no cloning theorem is one of these. Remember I said that one of the points of the field of quantum information is to kind of understand the difference between classical and quantum. And the no cloning theorem is kind of one of those big fundamental differences. And what it says is that while you can copy classical bits, you cannot copy qubits. And in particular, there's no device that will take an arbitrary state and map it to 2 copies of itself. OK? And the proof is very easy. This is just a consequence of the linearity of quantum mechanics. So suppose you had such a device. Well, let's take 2 states, psi and phi. And so psi would go to 2 copies of psi, phi would go to 2 copies of phi. But it could also work on the superposition of psi and phi, right? And so what is this equal to? Well, we can expand it out, and we get psi psi plus phi phi plus the cross terms, phi psi plus psi phi. OK? Now, the thing is, the linearity of quantum mechanics also tells you that for any allowed quantum operation, if you take the sum of these 2 things, it has to go to the image under this map is going to be the sum of these 2 things. Now, the sum of these 2 things is this part here. And you see we have some extra terms that are not in general 0. OK? And so that's a contradiction. So this machine cannot exist. It's maybe worth thinking for a second about how this relates to the classical property that you can copy bits. Right? Why is that allowed? I mean, after all, if you put kets around the 0 and the 1, those become quantum states. And the answer is, it's OK. It's actually OK to have a machine that copies 0 and a machine that copies 1. It's just that it can't also copy 0 plus 1. Right? So you can have a machine that copies in a basis, a particular basis. And for instance, the C0 can be used to do that. You just can't have one that copies arbitrary quantum states. OK? Questions about the no-cloning theorem? You've seen this before, I assume, right?
Not at psi, I think.
Not at psi. OK. So maybe some of you haven't seen it then. OK. So they must have done it in the foundations class, at least.
I wasn't there.
Yeah. OK. But it wasn't in the introductory quantum mechanics course. OK. So then that's why I did it, just to make sure. OK. So so the next thing I want to do is quantum teleportation, which I think maybe was in the introductory course. Yeah. But I still want to review it because it's a kind of a very basic quantum information protocol, and it gives you kind of a little bit of sense of how we start to use these circuit diagrams and these gates to do stuff. And it's also kind of important practically in the field of quantum information. OK, so quantum teleportation. The one, maybe this is also an important thing to do, is to introduce two characters who play a big role in the field, which are Alice and Bob. So we have Alice, who's going to be up here at the top, and Bob, who's going to be down here at the bottom. And Alice and Bob, well, in this case, they're not very far away, but you can imagine them being distant from each other, on the other side of the planet even, or further. And Alice has a qubit that she wants to send to Bob. Now, it could be that Alice could take this qubit, and maybe she has some optical fiber connecting her to Bob, and it's a very reliable optical fiber, so she can put it into a photon and put it in this optical fiber and send it through this optical fiber to Bob. Okay? So that would be one way to send this quantum state to Bob. The problem, of course, is that if the optical fiber is not as good as they like, or there's some other problem with it, then it might get there and get lost. It might not get there. It might get lost on the way, or it might have some errors in it or something like that. So what they'd like to do is they'd like to kind of have some more reliable way of doing this. And there's various options. There's quantum error correcting codes, which we'll talk about later in the class. But there's also this protocol called quantum teleportation, which is very simple. And the idea is that before they separated their each going their own way, Alice and Bob created an entangled quantum state, the state 0, 0 plus 1, 1. And Alice took the first qubit of this state, and Bob took the second qubit. And then that was when they were together. And then they went off on their own way, keeping these qubits with them. So now Alice and Bob share this entangled quantum state. And now that they have this state, they have another option for how to send Alice's qubit to Bob. What they can do is well, Alice will do a Bell measurement here. Maybe I should break this down, actually. Make sure I get it right. And so the point is that Alice is measuring this thing here is a measurement of the states 0, 0, plus or minus 1, 1, or 0, 1, plus or minus 1, 0. Okay? So it's an entangled measurement that she's making. And she can build that measurement out of this little quantum circuit, okay, where she does a C0 and a Hadamard and then measures each of the 2 qubits. And this is going to give her 2 classical bits. And once she does that measurement, she's going to call up Bob on the phone and say, I did the measurement, and here are the 2 bits. They're 0, 1, meaning I got one of these 4 Bell states. Say I got 0, 1 plus 1, 0. So Alice sends these classical bits to Bob. And then Bob is going to do one of the 4 Pauli matrices. And which one? So by what are the 4 Pauli matrices? Well, there's the identity. That's when Alice gets the state 0, 0 plus 1, 1. But there's also X, which is the bit flip, Z, which is the phase flip, and Y, which is IX times Z. And so depending on which of the 4 outcomes Alice gets, Bob will do one of these 4 Paulis. And the upshot is that at the end, Bob has Alice's qubit. OK? So notice that there's been no quantum communication directly between Alice and Bob. Right? They shared this entangled state to start with. But that entangled state is independent of the state that Alice wants to send. And then Alice only sent classical bits to Bob, just 2 classical bits. And if you think about it, 2 classical bits doesn't seem like it should be enough to contain all the information about psi, right? Psi is an arbitrary single qubit state, right? So there's an infinite and indeed uncountable set of possible states that Alice could have had. And 2 classical bits, 4 outcomes is not enough. But somehow all that infinite set of possibilities is contained in this entangled state. We've kind of split the quantum communication into a quantum part and a communication part. I mean, the other thing that's maybe a bit surprising about this is that in light of the no cloning theorem, Bob is getting a copy of Alice's state, which sounds like it might violate the no cloning theorem. But the catch is that in order to do this, Alice had to make this measurement which destroyed her copy of the state. So there's still only 1 copy, but it's been moved. It's been teleported from Alice to Bob. Yeah?
I don't understand about how by applying any of the elements of P, how do you get back psi?
Yeah. OK, maybe it's worth doing an example. Just kind of work it out. So I'm just going to do one of the cases. So let's see. So psi, we'll write it as alpha 0 plus beta 1. And 0, 0 plus 1, 1 is the state that they start with. So then psi tensor that is alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. And suppose Alice does her measurement and she gets 0, 0 minus 1, 1, just one of the possibilities. Turns out that all 4 are equally likely. So let's see. So we have to expand this as 0, 0 minus 1, 1 tensor other stuff. I don't want to do the whole calculation. Let's see. How can I short circuit it? So OK. So you notice if we have this term or this term, that's never going to project on 0, 0 minus 1, 1, right? Because these ones, so let's see. So the 0, 0 is 0, 0 plus 1, 1 plus 0, 0 minus 1, 1. That's the way to expand it. And the 0, 1 is the sum of these 2 things. These are the difference, right? It's the same thing, but in the opposite sign. So it's just going to be this term and this term that we care about. So we have, So these ones are the states phi plus minus, and these ones are the states psi plus minus, capital psi and capital phi. And so I'm going to write this as phi plus plus phi minus tensor 0. And then we have these terms, and we have also plus beta phi plus minus phi minus 1. OK? So I'm skipping these two terms just to save calculation. And so if we get phi minus in the measurement, we're projecting out this component. Right? The phi plus is when we get the phi plus state. And so, so if the bell is equal to phi minus, that means we now have the state, well, Alice, of course, has phi minus in her 2 qubits. And Bob, this is Bob's qubit here, has alpha times 0. And this is a minus sign here. So we have minus beta times 1. OK? And you see that if Bob does the z operation, the phase flip, 0 goes to 0, 1 goes to minus 1. And this gets back to alpha 0 plus beta 1, which is exactly Alice's state. OK? And if you work it out for the other ones, it's the same idea. Yeah.
In the beginning, when you start off with 0, 0 plus 1, 1, don't you need to clone that for Alice and Bob to each?
No, OK. So the point is this is a 2-qubit state. And so Alice is taking the first qubit of it, and Bob is taking the second qubit. Is the question, how do you make this state 0, 0 plus 1, 1?
No. I think you answered.
OK.
Yeah.
OK. But it may be worth saying how you make the state 0, 0 plus 1, 1, because that's, it's a good practice for quantum circuits. So how do we do that? Well, this state we can make with a very simple circuit that looks like this. So we're going to start with 2 qubits in the 0 state. And then we're going to do the Hadamard on the first one. So the first one is 0 plus 1. And then we do the C0 gate. And so we had 0 plus 1 tensor 0. And if we had 0, the 0, 0, 0 part goes to 0, 0. And 1, 0 goes to 1, 1. And so now we have 0, 0 plus 1, 1. OK? And in the tutorial today, you'll get more practice, not with this specific circuit, but with some other example quantum circuits. So you get maybe some more feel for how that works. OK. So quantum teleportation, so it is genuinely important if you want to do quantum communications. And one reason for that is what I said, which is that sending the qubit that you want to protect directly exposes it to the possibility of errors. Now, you can deal with quantum error correcting codes, but it turns out that it's actually better to try to establish a shared EPR pair, whether you're doing this in the way I said, where Alice and Bob were together and then moved apart, or if you're sending the qubit of the EPR pair through the channel. Because in that case, you know what you're trying to get, right? And if it, for instance, gets lost along the way, you can say, oh, well, let's forget that one and try again. And so it's easier to correct the case where you know that you're trying to create the EPR pair. And once you've done that, it's more reliable, and then you can use quantum teleportation to send the qubit. But teleportation is also useful in another other contexts. You can use it within a quantum computer to move qubits around from one part of the computer to another. And in fact, you can use it as kind of a building block for more complicated protocols, or even to do kind of non-trivial gates by kind of modifying this teleportation circuit a little bit. So it's really a useful thing to have and an important thing to know. OK. So are there any more questions on teleportation? OK, so in that case, here's another simple quantum protocol, which is called superdense coding. And superdense coding is actually closely related to quantum teleportation, but it's going the other way. So in quantum teleportation, we used an EPR pair and the transmission of 2 classical bits to send a qubit from Alice to Bob. In superdense coding, we're going to use an EPR pair and the transmission of a quantum bit to send 2 classical bits from Alice to Bob. So again, we have Alice and Bob. And again, they're going to start with an EPR pair. So it's the state 0, 0 plus 1, 1. And Alice, this time, has not a quantum state, but she has 2 classical bits. OK, that she wants to send to Bob. Now, of course, if Alice and Bob share a communication channel, she can just send those 2 bits. And that requires 2 bits of communication, of course. But what's surprising about superdense coding is that given this EPR pair, Alice can send those 2 bits to Bob with just 1 qubit of communication, which is showing that, in this context at least, a qubit is a more powerful communication resource than classical bits. Right? Even if Alice and Bob agree on whatever ahead of time, you could never send, in the classical context, you could never send 2 classical bits of information without sending at least 2 classical bits of information. Right? There's just not enough options. So how do we do this in the quantum case? Well, Alice is going to do one of the 4 polys based on her 2 classical bits. Right? And so at this point, this is kind of undoing this last step of Bob. So there's if Alice has the bits 0, 0, she's not going to do anything. She's going to do the identity. And then they'll have the state phi plus. And depending on which one of the other polys she does, they might get the state phi minus or psi plus minus. So they'll get one of these 4 Bell states. And the thing is, these 4 Bell states are all orthogonal states. Right? So again, there's a measurement here that can project on which of those 4 states she has. So that's what they're going to do then. She's going to send this qubit to Bob, and then Bob will make the Bell measurement. And then based on the outcome of that Bell measurement, he'll have the 4 possible states, and that will correspond to the 4 possible messages that Alice can send with 2 bits. OK? So of course, in some sense, there's really 2 qubits used here. Right? Because they had this EPR pair, and Bob had to get the second qubit of that somehow. So in some sense, you're not really saving. Right? There's still 2 qubits that are needed to send 2 bits. But the difference is that one of those qubits doesn't depend on the values of the bits. It could be sent ahead of time. Right? So you could imagine a practical use for this in a world where qubit communication is really cheap, as cheap as classical communication. You'd say, well, OK, I know that I'm going to Alice and Bob, they know that they want to communicate, or they will want to communicate. So at night, while they're sleeping, they're going to have their computers generate lots of EPR pairs. And then when they actually want to send the messages, they can do it by only sending half as many qubits. OK? But again, it's an example of how we can contrast the classical and the quantum. And putting teleportation and superdense coding together, you can kind of see that, well, in the presence of entanglement, a qubit is kind of equal to 2 classical bits. Right? If you don't count the cost of making the entangled state, you can convert back and forth between them at that rate. OK? Any questions on superdense coding?
Sorry, I have a simple question on the measurement that Alice does in quantum teleportation.
Yeah.
So that little circuit, which is kind of the inverse of the circuit that makes
Yeah.
bell pair. So I guess that just like rotates the basis from
From the bell basis to the zero. Yeah, that's right. Right. So yeah. So this circuit rotates from the standard basis to the bell basis, and this one kind of goes back the other way. Okay. So so next thing I want to do is something that I hope is review, which is to mostly so far we've been talking about pure states. Remember, mixed states though did show up very briefly yesterday. And so I want to review kind of the quantum formalism for mixed states, because it's not usually covered in undergraduate quantum mechanics. So that means density matrices, that means CP maps, and it means POVMs. So I think you saw all of these before, but I figured it would be worth going over them again. This is something that I really think every physicist should know, regardless of whether they're interested in quantum information or not. But somehow it's not always taught. OK, so mixed states, remember, you can think of them as probabilistic mixtures of pure states. So you might have a situation where you have an ensemble where you say, well, with probability pi, we have the state psi I. OK? And we represent that as a, if it's a d-dimensional Hilbert space, it's a d by d matrix. And they're frequently written as rho or sigma. And in this case, we have we would write it this way, right? Because this ket followed by bra, that's an operator. It's a linear operator, and therefore you can interpret it as a matrix. And of course, you can expand this in some basis. And to make the matrix form explicit, and then in that basis we have this matrix rho AB, which is a d by d matrix. OK, so under unitary, that maps rho to u rho u dagger, right? Because if we do a unitary, psi I goes to u psi I, but the bra psi I goes to psi I u dagger. OK? These matrices here, so the density matrix, because it's the probabilities are all non-negative, and they sum to 1, the density matrix is a positive matrix with trace 1. OK? So one way you can always represent this density matrix is by choosing a change of basis u to diagonalize rho, because positive matrices can always be diagonalized. And then you can find a representation here where the psi I are an eigenbasis of rho. And so they're all orthogonal to each other. And these probabilities, then you can think of is just the probability of things drawn from this particular eigenbasis. OK? Right. And so in that representation, you can immediately see that the trace has to be 1. Right? Because if we've diagonalized it, we have probabilities of each of the things along the diagonal. The sum of those probabilities has to be 1, which is the trace. And the trace is a property that's invariant under unitaries. So if it's trace 1 in that particular basis, it's trace in 1 is in any basis. Is 1 in any basis. OK? Right. OK. So what happens if we have a bipartite system? Well, if we have a bipartite system, rho AB, well, we could write that in terms of the tensor product basis. Like this. And from this bipartite density matrix, we can derive the density matrix for just one part of it. The state rho A is going to be the trace over B of rho AB, which AA prime. And so the density matrix for that is sum over C of AC A prime C. OK? And so while I said you can think of as density matrices derived from these probabilistic ensembles of pure states, you can also think of the density matrix as something that's derived by tracing over some bigger system. And the reason for that is because, well, what happens, I mean, this was an arbitrary density matrix. But what happens if this initial state is a pure state? Well, if it's a tensor product state, then that's fine. Tracing over one part of it, that just gives 1, and we get another pure state. But if this is an entangled state up here, then when we trace over part of it, we get a mixed state. And moreover, for all density matrices rho A, there exists some pure state on A and some other system R. R is called the reference system, such that rho A is the trace over R of psi. OK? So I think you've seen this before, but are there questions on it? Yeah.
So the dimension of R has to be equal to A?
Dimension of R, yeah, could be up to, yeah, if the dimension of A is D, then R could also be size D. And in general, it has to be. Because like if you take, so if rho A, for instance, is the maximally mixed state, it's a uniform, it's just a diagonal matrix, 1 over D on all the diagonals, then the purification is a maximally entangled state, which is sum of over A of A tensor A. And that has D terms, so you can't avoid that. So I should say that this purification is not completely unique, but it's kind of almost unique. So it's unique up to unitaries on R. And unitaries on R will not affect, because unitaries, again, trace is invariant under unitaries. So if you do a unitary on say, B up here, that's not going to change what this rho A is. And it shouldn't, because rho A represents the state of A, and doing something on B, which could be very far away, should not change the state of A.
So it's unitary on R. So if I think of, say, the Bell states, and I trace out the second one, then I get some. You
always get the maximally mixed state. But you notice that all those 4 Bell states can be gotten between them by applying a Pauli on just one side. Yeah. And that's exactly what we're taking advantage of for superdense coding and to a certain extent for teleportation. OK? OK, that's 12:30. So maybe I'll stop there. And then tomorrow I'll continue with CP maps, POVMs, and some other properties like of quantum states, specifically fidelity and trace distance. And then maybe start on implementations if we have time. OK, but are there questions on stuff we did today? OK.